So quick review of the stuff we covered there the day before the Christmas break. Okay, we talked about the two types of waves, transverse waves and longitudinal waves. All right, so as a quick review, a transverse wave is one in which the medium oscillates perpendicular to the direction the wave travels. All right, so a water wave or a tidal wave is an example of a transverse wave. The water oscillates up and down while the wave travels forward, backward, left, right, okay, whichever. Okay, so those motions are perpendicular to one another. Right, that is a transverse wave. Okay, follow on that. Okay, a longitudinal wave, okay, looks a bit different because a longitudinal wave, okay, is a series of compressions and rarefactions. So that means that the motion of the medium is back and forth, and the wave travels parallel to it. Okay, so the wave would be traveling forwards, and the medium would be oscillating back and forth, back and forth. I'm going to show you both of these with a spring here in just a minute. Okay, so longitudinal wave, okay, has compressions and rarefactions. Okay, it looks something like this, but I'll show you what it looks like here in just a second. If I've got these compressions and rarefactions going back and forth, okay, then that can cause, again, like I said, changes in pressure. Okay, not a lot of waves are longitudinal. Okay, sound waves are longitudinal, and there are certain types of seismic waves that are the result of an earthquake that are longitudinal. Okay, earthquakes actually produce both types of waves. They produce some that are transverse, okay, that makes the ground go up and down, okay, and there are some that are longitudinal, okay, that actually compress and stretch the earth, okay, and those can be very damaging. So can the ones obviously that go up and down, okay, those are the ones that topple buildings and things like that, okay. So longitudinal waves, less common. Now here's the weird thing. Transverse waves travel best through less dense materials. Longitudinal waves travel best through dense materials, okay? Which is why sound actually travels slowest in air, but exceptionally fast through water or wood or whatever. Okay? The more dense a material, the better the longitudinal waves will travel. Whereas transverse waves travel better in materials that are not dense because they require the particles to do a lot more.
So if you were in an earthquake, would you get like longitudinal waves first? And then
you know what? I can't remember which one travels faster. There's actually like 3 different types of waves that travel. 2 of them are transverse and 1 is longitudinal. I don't remember which one's fastest. There's some that travel really fast but dissipate quickly, and there's some that travel slower but they can rebound. Those are the ones that cause the aftershocks. So an aftershock can be caused by the fact that the waves travel through the mantle, reflect, and then come back. Yeah, crazy. Okay, everybody clear on the 2 types of waves? Okay, the other thing to remember that we didn't review here quickly is that a wave is not matter. A wave is energy. Okay, it is a traveling disturbance. Okay, it travels through matter, but is not matter itself, which is why, because Gavin, you were asking us, if we both made waves in the slinky, would they bounce off each other? The answer is no, they won't. They travel right through each other. Okay, because they are not matter. They're energy. Energy can do that. Okay, if I push 2 cars towards each other, they smash into each other. They're matter. They can't occupy the same space at the same time. Waves, because they are energy, can. And actually that's what causes interference. And we're going to look at interference, not today, but probably tomorrow. Okay? Interference is what happens when 2 waves do occupy the same space at the same time. Okay? What happens to the medium, what happens to the waves. Okay, we'll look at that. All right. So, like we said, in a longitudinal wave, we got alternating disturbances, okay, and they travel parallel to the direction of the wave. So if we were looking at a marked link on the slinky, okay, as the compression moves in, that piece of the medium would move forward. As the rarefaction passes, that piece of the medium moves backwards, but that piece of the medium doesn't travel that way. It just oscillates back and forth. Okay, and we said the same was true for transverse waves. The medium moves up and down. Okay, the wave travels this way, right? Which is why the ocean doesn't have a hole in the middle. Okay, we talked about that in December. We said because the ocean actually only moves up and down, the waves are actually what travels forward and backward. Okay, the water all kind of stays in the same place. Okay, if the water actually moved with the wave, all the water would end up on shore and there'd be a big hole in the middle of the ocean. Okay, because the water would be going. It doesn't. The water just moves up and down. The waves travel through the water, okay, on their way to somewhere else. Right? And that's the thing that we have trouble getting our head around, because, and I showed you guys those videos before Christmas of the tidal waves. Okay, we see these waves, we picture them coming in and they go inland, and that means that the water has to be moving from one place to another. Okay, it isn't. It's being disturbed, and when it gets disturbed, it moves upwards, and then when the wave leaves, there's this column of water that's now unsupported, and it just falls back down. And it's actually the splash, okay, that causes that that water to move in. Okay, so some properties of waves. Okay, wavelength. So if we're looking at a wave like simple harmonic motion, okay, because it is an example of simple harmonic motion, the length of one cycle, okay, is known as the wavelength, and we symbolize that with the Greek letter L, or lambda. Okay, so the Greek letter lambda is actually the equivalent of L. Okay, now it looks like, when you actually look at a picture of lambda correctly, it kind of looks like this. Okay, that takes a long time to draw. So lambda is a long stick supported by a short stick. Okay, that's what lambda, just write it that way. Okay, it's a lot quicker. Okay, it stands for the length in meters of one wave or one cycle of the medium. Okay, the amount of time it takes for that wave to go by is period. The number of waves that go by every second is the frequency. Okay, so a lot of the same terminology as pendulums and masses on springs, because a wave is just a medium oscillating with simple harmonic motion, just like a mass on a spring. Okay, the maximum distance that the medium moves from its undisturbed or equilibrium position is also called the amplitude, just like it was for a mass on a spring or a pendulum. Okay, so we're using all of the same terminology. The only thing that's new is wavelength. Okay, because we don't measure the length of a cycle for simple harmonic motion. Okay, so amplitude, like we said, is maximum excursion of a particle of the medium from the particle's undisturbed position. Okay, the amplitude is the distance between a crest, which is the highest point, or a trough, which is the lowest point, and the undisturbed position. Okay, so this here, that's a crest. Okay, this here is a trough. Okay. They're the same distance from equilibrium, just one's positive and one's negative. Okay. Now, wavelength, like we said, is the length of one complete cycle. So, that's one cycle is the distance between any two equal successive points. Okay? So, if I move this line that I just drew, okay, you can see that as long as I keep moving it along the wave, it always touches the next equal point on the wave. Okay? So any two equal successive points on the wave are one wavelength apart. So one crest to one crest is one wavelength. One trough to one trough is one wavelength. Okay? Or any other equal points on the wave, okay, are going to be one wavelength apart. All right. So we just talked about wavelength. Okay. The time for one wave to pass you is its period. The number of waves that go by every second is the frequency. Okay. We talked about that already as well. Okay. A good analogy of this is actually a train. Okay. So if you're standing beside the tracks, watching a train go by. Okay. The length of a wave would be like the length of one car. The time for one car to go by would be like the period of the train. So. Okay, assuming each car is the same length, okay, things like that. All right. Okay, so like we said, waves are an example of simple harmonic motion because they repeat over and over, just like a mass on a spring or a pendulum does. Okay, so it's shown below. If I have a mass on a spring that's oscillating, and I showed you that video of the oscillating spray paint can, okay, it makes a wave pattern, right? So any simple harmonic motion is going to make a sinusoidal or transverse wave type pattern. Okay. All right, so next thing we're going to look at is some of the really easy math to do with waves, okay, and that is the universal wave equation. So that's this. V equals F times lambda, or lambda over T. It's the same thing. So we can calculate the speed of a wave if we know its length and its period, okay, or its length and its frequency. Either one will get us the speed of the wave. All right, is that going to be a very hard formula to manipulate? On your formula sheet, it's only written this way. Okay, V equals F times lambda. Okay, but obviously since F is 1 over T, it could also be written as lambda over T, which would be the same as lambda times 1 over T. Okay. All right, now, weird thing about waves. Once a wave is produced, 2 of the 3 properties can change. 1 can't. Once a wave is produced, its frequency cannot be altered. And it will always have the same frequency. That cannot be changed. It is controlled by the source of the wave. But waves can change their speed. If their speed changes, so if this number changes, but this number can't change, what does this number have to do? It's got to change as well. All right? So if I manipulate this formula for F, it's going to be V over lambda. If V doubles, what does lambda have to do? It's got to double. Okay? If F is going to stay the same, if V changes, lambda has to change in exactly the same way. Right? That's the only way that F can remain the same. Now, I'm going to say frequency never changes about 100 times over the next 3 days. It's really important that you remember frequency of a wave can never change once it's produced. Think about like 6. Okay? It's really important to know that the frequency of a wave can never change. Right? Speed and wavelength can. Right? And we can actually see kind of an example of that. If we look out, just out here, where the speed limit inexplicably changes from 100 to 60, okay, and we look at cars as they travel through there, they behave just like a wave would behave. Right? So if I have 3 cars in a row out here, traveling at 100 kilometers per hour, and then a little while later, I see those same 3 cars in the 60 zone, how are they going to look? Okay, the cars themselves, yes, will look the same. They're going to be closer together. Why? Exactly. This car hits the 60 zone first. It slows down. This one hasn't slowed down yet, so it's going to catch up. Then it'll hit the 60 zone. Okay? So a little while later, I'm going to see this. I'm going to see those same 3 cars. But now they're traveling slower and are closer together. So if I look at the distance between them like wavelength and their speed as speed, okay, here the speed has decreased and so has the wavelength. Okay? The same thing happens to waves. When a wave goes from one medium to another, its speed can change. Okay? It is actually the medium in which a wave travels that controls its speed. Okay? So when a wave travels from a fast medium to a slow medium, it obviously slows down and it gets shorter. Okay? Its wavelength decreases. But the frequency between the waves will stay the same because they've slowed down and gotten closer together. This is actually what causes tidal waves to become so large near shore. Okay? A tidal wave out in the open ocean where it's really, really deep might only be a couple of meters high. Okay? Because it's caused by an earthquake. Okay? And it basically is caused by a piece of earth that's pushed upwards or drops really quickly, one or the other. Okay? And that disturbance is only going to be a few meters. But once that wave gets to the shallow part of the sea, okay, so out here is deep water, okay, and like this would be the shallower part here. Okay, so out here, that tidal wave might only be about this tall. Okay, but as it gets closer to the shore, it slows down. Okay, because the water gets shallower. So what happens is the front of the wave slows down, but the back of the wave doesn't. Not right away, at least. And so as a result, the back of the wave catches up and squishes all that wave energy into a smaller, shorter wave. The only place for the wave to go is, okay, which is why a tidal wave gets really, really tall as it approaches the shore. Sometimes you don't even see them in the open ocean. Okay, the little sensors that they have to detect them actually have to be very sensitive in order to detect a wave like that. Okay, so go over that next part. Okay, so the universal wave equation and the transmission or traveling of waves. Okay, so what affects the speed of a wave? The medium. Okay, the medium in which a wave travels affects the speed of a wave. Okay, so if you ever made one of those little phones when you were a kid, you guys probably didn't because you probably had a cell phone. But okay, as a kid, we would like take 2 soup cans, right, and we put holes in the bottom and then tie a string between them. As long as the string was tight, you could talk to each other. You probably didn't do that because you weren't cool. You had phones, you were too cool. Okay, but that works because the waves. Okay, I would talk into one can. I would make the air inside that can vibrate. The vibration of the air makes the can vibrate, which vibrates through the string, goes to the other can, and that can vibrates and then turns into the air, and the person on the other end can hear. As long as the string is tight, it works. If the string is loose, it doesn't work. Okay, but that's waves traveling through. Now, they travel very slow in the air, but very fast through the string. Okay, so there's not a big delay. If I was talking through the can, the sound would get to the person listening faster than if I shouted to them across the same distance. Okay, because the waves would be traveling through a different medium and would, as a result, travel faster. All right, and then we'll look at and use the universal wave equation. Okay. So, like we said, the medium can affect the speed of a wave. And a place where we use this is actually in jewelry, right? In the cutting of like precious stones and especially diamonds. Okay? Light is a wave. So if I have a stone, like a diamond, okay, that's even like roughly symmetrical, okay? If I want it to sparkle, where do I want the light to come out? The top. Okay? Now, light can come in through the top, but I want it to all come out through the top as well. Okay? So what a stone cutter does is they know the material they're working with, and they cut it at a certain angle to cause the waves to not escape. So as light comes into the diamond, it slows down, because diamond is way more dense than air. Okay? It significantly changes the speed of the light waves once they enter it. Okay? And so what they do is they bend. Okay? When light slows down, or any wave slows down, it bends. Okay? So it bends and it hits this facet. Any side on a stone is called a facet. Okay? If it's cut right, there's a certain angle that will not allow light to escape, and something called total internal reflection will occur. Okay? That light will bounce off of this facet and hit this one, and it won't escape. It will bounce off and come back out the top. Okay? Any light that comes in through the top or the sides is treated in exactly the same way. So any light coming through this facet, this one, or this one will reflect off the bottom and come back out through the top, making the gem sparkle. Okay? If it's not cut right, it will sparkle. Okay? Now, that's how you do that for a diamond. What do you do for a cubic zirconia? It's a fake diamond.
Different angle.
Different angle. Exactly the same science. Different angle. Now, a stone cutter can tell a real diamond from a fake diamond immediately. They don't look at the stone itself. They look right here. That's all they have to look at. And they can tell right away whether you cheaped out, and you're going to be in really big trouble if you did. Okay? Or you bought the real thing. All they have to do is look at that angle. Okay? They'll know right away. Because a cubic zirconia has to be cut way wider than a diamond. Because glass doesn't slow down light nearly as much as a diamond does. Okay? So they can tell right away, just by looking at the bottom of the stone, whether it's real or fake. So don't cheap out. Okay? I was smart. My wife was worth it. I bought it real life. If you're cheaping out, consider whether
Is the initial angle it hits the same angle as it comes out by?
Up here at the top, you mean?
Yeah.
Most likely, yes. Okay, now something that can affect this is if I put the diamond underwater. Okay, diamonds are cut to sparkle in air because that's where they are most of the time. If I put it underwater, now it's not going from air to diamond, it's going from water to diamond. That changes the speed. Okay, and as a result, diamonds and other stones don't sparkle as much underwater as they do in the air. They're not cut for that. Okay, so this has to do with waves. The speed of a wave is affected by the medium in which it travels. Okay, so anytime it changes media, it's going to change its speed. Okay, so how fast does a traveling wave move? Well, if we knew how far it traveled and how long it took, we could just go V equals d over t. Agreed? Okay, that's kind of hard to do with a wave because a wave doesn't really have defined parts. Like if you're watching a wave travel in the water, can its shape change quite a bit? It's really hard to measure where it starts and where it ends and how far it's gone and how long it took. There's not a lot of reference points or anything like that. Okay, so it's tough to actually use that formula. We could, okay, but it's a little tougher to do that. Sometimes it's easier to use the properties of the wave instead, which is where the universal wave equation comes in. Okay, it is important to know that the speed of a wave is dependent on the properties of the medium in which it is traveling. Okay, so the medium and the medium's properties. In fact, if we're talking about sound waves, even the temperature of the air can affect the speed of sound. Okay? Speed of sound in air at 0 degrees Celsius is 332 meters per second. But at room temperature, it's 343. Okay? So even the temperature of the air can affect the speed of a sound wave. Okay? And the same is true for all materials. It's the properties of the material that determine the speed of the wave. If we're talking about water, it can be the depth of the water. Okay? The deeper the water, the faster the wave will be, the longer the wave will be. But as the waves get closer to shore and the depth decreases, the wave rears up because it gets slower and shorter, and it still has to conserve all of its energy. Okay? So it's slowing down and it's turning its kinetic energy into potential energy, getting taller. Okay? Energy is conserved, okay? And so we squish the wave and make it get taller. Okay? Everybody all right with that? Okay, so if we're looking at the universal wave equation here, okay, we said that we can use it in this form, but on your formula sheet, it's actually written as V equals frequency times wavelength. Now, if I do that, what are the units for frequency? Hertz, or cycles per second, okay? And what are the units for wavelength? What do we usually measure length in? Meters. So I'm going to have per second times meters is going to be meters per second. Okay, so we do get the right units. Okay, same thing here. Period is in seconds. This is in meters. Meters divided by seconds. Meters per second. Okay, so that'll help us to determine, okay, the speed of a wave using that equation. All right, so if I have a sound wave that has a frequency of 262 hertz, okay, so they gave me F, and I know the wavelength is 1.29 meters, okay, I can very quickly calculate the speed of the wave. I just take F and lambda and I multiply them together. Okay, speed of that wave would be 338 meters per second. Okay, everybody all right with using that formula? Okay, now there's some tricks to this formula. Okay, obviously it's a 3-variable formula. Manipulation is not going to be your primary issue here. Okay, your primary issue is going to be in the wording of the questions. So, as an example, I could give you a question that sounds something like this. Maybe write this one down as an example. If I have to tell you how long they are. Actually, I'll put it a different way. I got too many fives on there. 6. Okay. So, the question is saying this person is on a boat and they see 5 crests go by. Okay? So the crest is the up part of a wave. Okay? They see 5 crests go by in 32 seconds. And we know that the waves are 6 meters apart. What have they given me in this question? Okay, they give me wavelength. 6 meters. What else? Okay, yeah, so I've got a way to calculate either frequency or period, okay? But here's the mistake people will make. They'll assume the number of crests is the number of waves. It's not. Okay, and that's the trick that can creep in here. So I'm going to draw what 5 crests looks like for you. Okay, so the person starts counting here on the first crest. This is 1 wavelength. This is 2 wavelengths. 3 wavelengths. How many waves are there? If I see 5 crests, I only see 4 waves. Okay, that's one of the few tricks that can come up here. Okay, is that in 5 crests or 5 troughs, okay, there are actually only 4 waves. Had the question been worded, the person is on a boat and oscillates up and down 5 times, then how many waves are 5? 5. Okay, because it said they went through 5 complete oscillations. Here, they only saw 4 complete oscillations because they counted the crests, not the cycles of the wave. Okay, so something to watch out for. Okay, so now I can calculate the frequency, because that's what I want to use. Okay, that's going to be cycles per second. Right, so that's going to be 4 cycles divided by 32. Okay, all right, so when I go 4 over 32, that's going to be 20. Okay, so our frequency is 0.125. 0.125 hertz. So less than 1 wave per second, which makes sense. There were only 4 waves in 32 seconds. It's definitely less than 1 wave. Okay, all right. So now that I've got frequency and wavelength, can I calculate the speed of the waves? Yes. Okay, so V equals F times lambda. So I take my 0.125 hertz and I multiply by the length, which is 6 meters. Okay. So these are obviously pretty slow moving waves. Okay, so they're moving at 0.75 meters per second. Okay, so universal wave equation problems are actually pretty easy as long as, like mathematically easy, as long as I pay attention to what the question tells me. Now, other things the question might tell you could be things like you're dealing with a radio wave. How fast is a radio wave traveling? Very fast. How fast specifically? A radio is an electromagnetic wave. Electromagnetic waves travel at the speed of, not sound, light. Okay, all electromagnetic waves. Okay, that would be infrared. Okay, electromagnetic, whatever. Okay, they're all going to travel at the speed of light. Okay, speed of light is on your formula sheet under other useful constants. It is 3.0 times 10 to the 8 meters per second. Right, so anytime you're dealing with an electromagnetic wave, light wave of any kind, that is its speed. Okay. Another thing that can come up is it might give you something like a sound wave is traveling through air. The temperature of the air is 15 degrees Celsius. How does that help? Does the speed of the wave, is it affected by the temperature of the air? It is. So on your formula sheet, you'll also find this formula. This helps you to calculate the speed of sound in air at any temperature. All right, so this T here is the temperature in degrees Celsius, which is why if it's a negative number, you'll actually be subtracting and the speed will slow down. Okay, everybody follow me there? So if you're given sound waves and it gives you a temperature, you're going to have to refer to this formula to get the speed of the waves.
Does that work for light too?
No. Light always travels at 3.0 times 10 to the 8. In air,
In a vacuum.
in a vacuum, and in air, we assume them to be the same. We're not going to take Snell's law this year. You'll take it next year where you can calculate the speed of light in various materials because it's different. That's the speed of sound at 0 degrees Celsius. Remember, I just told you on there you go. Okay. So, speed of sound in air at 0 degrees Celsius, 332 meters per second. You go higher than that, it'll speed up. You go lower than that, it'll slow down. Okay? Everybody with me on those?
Does the Doppler effect have something to do with waves?
Yes, it does. And it's the last thing we're going to talk about in this unit, but we're not there yet. But yes, it does. Okay, so I'll go over a couple here. Let's look at this one here. I want to generate waves in a stretched spring. So I oscillate my hand back and forth at a frequency of 2 hertz. Okay? So what did they just give me there? Frequency. Okay? The frequency is 2.0 hertz. Okay. Speed of the waves is 5.4 meters per second. What's the wavelength? So we're looking for lambda. Okay, well, V equals F times lambda. Okay, so I divide both sides by F. That'll leave me with lambda 5.4 divided by 2. That should give me 2.7 meters for the length of my waves. Okay, fairly easy formula to use. That's about as easy as a universal wave equation question would get. Okay, generally they're going to have some kind of little trick in like the crests or the speed of light or the speed of sound or something like that. Okay, I want you guys to try these ones. I'll make them bigger so you can read them. Okay, let's try 1 and 2 for now, and then we'll go over those and have a look at 3. Okay. So for number 1 here, okay, we're given the frequency, 440 hertz, and we're told the speed of sound in the auditorium is 350 meters per second. Okay, so we're looking for lambda. So lambda will be V over F. Okay, that'll be our 350 divided by 440. Okay, and that'll give us our wavelength. Okay, so 350 divided by 440 gives us a wavelength of 0.795 meters, 0.795 meters. Okay. All right. How many people have done number 2? How many people are stuck on number 2? Okay, let's have a look at number 2. Here's what we have to think about. Okay, we've got here's the surface of the water. Here's the submarine. It's not bad. Okay, and here's the bottom. Okay, so we've got sound waves that are headed to the bottom. They hit the bottom, and then their echoes come back. How far do the waves travel? Twice the distance they're asking for. Okay? They want to know how far is it from the submarine to the bottom. But they tell you it takes 8.5 seconds for the sound to come back. How long does it take the sound to get there? Half that long. Okay? So you either got to calculate the total distance traveled and divide by 2, or divide the time by 2 and then calculate. Okay? So here's what we have. We're trying to calculate this distance. In order to calculate that, I need to know, okay, the speed of the waves. So I'm going to calculate that first. V equals F times lambda. And I'm going to take that frequency, 325 hertz, multiply it by the wavelength, 4.71 meters. Okay, so the speed of sound in water is like 1.5 kilometers per second. Okay, so sound travels way better in water than it does in air. Okay. So there's my new speed for the waves, for the sound. Okay. Now I want to calculate how far it is to the bottom, and I know that the time it takes to go there and back again is 8.5 seconds. That means the time it takes to get here is only half that, 4.25. Okay? So D equals V times T. I take my 1,530.75 and I multiply that by 4.25, the time to get just to the bottom, okay? And I'll have how deep the water is. Okay? So 7.27 times 10 to the 3 meters. Right? It's very deep. 7 kilometers. Okay, pretty deep. All right, everybody follow me on that one. Okay, so those are echo questions. Anytime you're dealing with an echo, remember that an echo has to travel there and back. Okay, just one of those little tricks that you gotta watch out for. Okay, question that has another. Okay, we got a person that's in a dinghy. Okay, one of those inflatable rubber boats. Okay, 250 meters from shore, the dinghy rises and falls 8 times per minute. Okay? He finds that it takes a wave 3 minutes to reach the shore. How far apart are the wave crests? Okay, wave crests are always how far apart? One wavelength. That's what you're being asked to find. Okay? The distance between 2 crests, 2 troughs, or any 2 equal successive points on a wave is the wavelength. So you're trying to find wavelength. They're giving you some information that they can help you find that. So I'm going to give you a couple minutes on number 3, and then we'll go over that one. So, for question number 3, first thing they tell us is a distance. Okay, it's not a wavelength, that's a distance. That's how far the waves are going to travel, 250 meters. Okay, the dinghy rises and falls 8 times per minute. What can I use that for? Period or frequency. Okay, it's telling me in 1 minute it went up and down this many times. That's cycles per minute. I can turn that into cycles per second by dividing by 60. Yeah, exactly. Okay, so I'm going to get the frequency here in hertz by simply going 8 over 60. Okay, and that'll give me my frequency. So 8 divided by 60. All right, so 0.13 repeating. All right, the last thing it says is that it takes 3 minutes to reach the shore. That's 180 seconds. Okay, so I've got distance and time. What can I use that to find? I can find speed. Right. Okay, so V equals D over T. Okay, 250 over 180 seconds. Okay, so we're looking at 1.38 meters per second. Now that I know the speed of the waves and their frequency, can I calculate the distance between crests? In other words, the wavelength. Okay, so wavelength equals V over F, 1.38 divided by 0.13. Okay, so we're going to get 10.4. Actually, we only have 2 significant figures here because that's okay. So 10 meters is my wavelength. All right. So in a universal wave equation kind of question, you're often going to have V equals D over T. You're going to get some of that stuff about how many crests, and maybe some stuff about echoes and things like that. Those are all examples of universal wave equation type problems. Okay. Okay, let's have a look just here at number 6. So we already know that the properties of a medium can affect the speed of a wave, okay, including temperature. So temperature, so we have a wave of the length of 2 meters traveling at 1,500 meters per second. Then it reaches a section of warm water where the speed is greater. So if the wave speeds up, will the wavelength get longer or shorter? Longer. Because remember, this is the about the 20th time I've said this today, frequency never changes. So if V changes, lambda changes in the same way. Okay? Always have to change together. All right. I want you to try that one. Same idea. Frequency never changes. Important for solving this one. This one will require you to think a little bit, but frequency never changes. Okay, so all there is to this one is two separate universal wave equation calculations using the different speeds of the waves in water and air. Okay, the frequency is going to be the same underwater and in air. Okay, that's actually pretty important because that's the second part of the question. If the frequency is the same, then the person hears the same musical notes. Okay, if you've ever watched like synchronized swimming, you don't have to admit whether you did or not, but okay, if you ever watched it in like the Olympics or anything like that, they actually have, I mean, some of the swimmers are above water, some of the swimmers are underwater at the same time performing like their routine. And if you've got like the big team one where there's like 8 of them, it's pretty important that they're hearing the same sound above the water and below the water so that they can remain synchronized. Okay, and so you would actually hear exactly the same musical note. Okay, whether you were in the air or whether you were underwater. Now, that doesn't mean it sounds exactly the same. Our ear is not designed to hear underwater like it is in air. Okay, we don't live underwater. Okay, so our ears don't work as well, but it should still sound about the same. Okay, so all we have to do is calculate wavelength. So wavelength will equal V over F. Okay, for air, that's going to be 350 meters per second. Okay, divided by the frequency, which was 384. Right, so our wavelength in air is 0.911 meters, but underwater, okay, where our speed is 1,500 meters per second, okay, we've got 1,500 divided by 384, right, and our waves are much, much longer. Okay, everybody all right with that? Okay. All right, so I'm going to have you guys work on a few of these to kind of finish class off, although there's only about 4 or 5 minutes here. Okay, because tomorrow, today is Tuesday, but you won't have a quiz. I'm going to quiz you on Thursday. Okay, tomorrow, obviously, today we're going to be going over some more stuff to do with waves, wave behavior to boundary, waves occupying the same space at the same time. I'm cramming a lot of stuff in, okay, in these last few days, so it's unfortunately going to be a lot of me talking and you listening. Okay, over the next few days, so just kind of be ready for that. Okay, so I'll put up the questions I want you to do up on the board here, and you can work on those until the bell goes. Okay, but that's what I want you working on there for the remainder of class. Okay, see how you do with those. Guys, by the way, units here. Be on the lookout for units. They give you some things in centimeters, then they give you like kilohertz or megahertz. Remember your metric conversions. Kilo means 1,000, mega means 1,000,000. Okay, so keep that in mind. Okay, when you're doing your metric conversions.